Good morning, students. Welcome to Wednesday, April 15th, 2020. Time for some physics. Woo! All right, today's learning targets. We're going to talk about energy. All right, so I want you to be able to define, describe, and calculate these different energy terms. So just playing out with energy, kinetic energy, potential energy, gravitational potential energy, elastic potential energy, and mechanical energy. We'll get all these terms as we go along. So, what is energy? I want you to think about it. That's actually a fairly complicated thing because we know different types of energy. All right, I've listed some: gravitational potential, elastic potential, kinetic. We've got solar energy, electrical energy, thermal energy, nuclear energy, chemical energy. There's a lot of different types of energy. We talk about saving energy, we talk about conserving energy, energy crises. We got lots of energy things. What is it all? Well, it's this hard thing to pinpoint, but here's what it all has in common. When you have energy, you can cause a change in something. And that is the definition that we use in science. Energy is the ability to cause a change. All right, so in physics, right now we're going to deal with three pretty specific types of energy. One is going to be kinetic energy, and I believe you've heard that word kinetic. I think you've heard kinetic energy before in previous science classes, and so I think most of you have a concept. But the word kinetic means moving. Okay, so kinetic energy is energy an object has due to its motion. So right here I have a tennis ball, and if I were just holding this tennis ball, it's not scaring anybody. But if you were sitting here in this room and I took the tennis ball and I went like that, you'd probably flinch. Okay, because through your years of human experience that if the tennis ball is moving, and in particular if it's moving towards your face, that tennis ball has some sort of energy in that motion, and it can bonk me in the head, and might not feel the best. All right. Now, also, we could compare. Got a tennis ball and I got a shot put, and if the shot put and tennis ball came moving at you at the same rate at the same time, you might kind of understand that the shot put is going to do more damage than the tennis ball. So if the two of them are moving at the same rate, it's kind of like, imagine that, it's after school and there's, let's say we were in school and there was track practice going on and weather was bad outside, so they're in the halls, and let's see, Bailey is sprinting down the hall and Caleb is sprinting down the hall. And let's say they're both going the same speed. And I'm not paying attention, and I walk out my classroom door, and here they come. Who would hit me harder? Well, if they're going the same speed, Caleb would hit me harder. But that's not to say just because you're heavier, you get more energy. It's a combination of the size of the object, the mass of the object, along with its velocity. Kinetic energy is the energy an object has due to its motion. So it's going to depend on the object and on the motion. And the way we calculate that in physics is with the formula kinetic energy is equal to 1/2 mv squared. So m is the mass of the object, so depends on the object. Bigger the object, the more massive the object, not bigger in volume, but bigger in mass, the more energy something has, and its motion. Velocity. Now, if it's not moving, it has no kinetic energy. Now, we said for calculating work, the unit of work was the joule. Well, the unit of energy is also the joule. Take a look at the formula we just had. Mass is measured in kilograms. Velocity is in meters per second. There's a square and a velocity, so I'm going to have kilograms meters squared per second squared. Well, that's the same thing we had when we said we had a joule is a Newton times a meter. It's a kilogram meter squared per second squared. So energy and work are two sides of the same thing. Okay? Basically, when you do work, you increase energy on an object. Oh, yeah, we said that already. Okay? Another energy label that you're probably going to see sometimes is calories and calories. And I'm not stuttering here. That's calorie with a little c. 1 calorie is equal to 4.184 joules. And then you have calories with a big C, which are also called food calories or kilocalories. So when you look at a label on a food package and it says 180 calories, those are food calories. It's actually 180,000 of these little calories, and then multiplied by 4.184 joules, you see that little food package, my granola bar package that I have in the morning has about 750,000 joules of energy in it. That would be in the form of chemical potential energy. We're not talking about that one right now. All right, so example problem. What is the kinetic energy of a 0.120 kilogram baseball flying towards home plate at 38.9 meters per second? Well, kinetic energy equals 1/2 mv squared. Okay, we're going to add this to our arsenal. Okay, hopefully you've got an equation list that you keep handy for physics. Add this one to it. So that's 0.5 times, what's my mass? 0.120 kilograms times velocity, 38.9 meters per second, times 38.9 meters per second. Because if I write it down twice, I'm not going to forget it in my calculator. We look at labels. Kilogram times meter per second squared is a Newton. Newton times a meter is a joule. Punch the numbers into the calculator. Now notice I replaced the half with a 0.5 because I just thought it was going to be easy for my calculator, but I certainly could have taken this and just divided by 2. Same thing. 0.5 times 0.120 times 38.9 times 38.9 equals, and we got 3 sig figs, so I've got 90.8 joules. Pretty basic, straightforward problem. Folks, if you haven't already got here, please get in the habit. You write down a formula you're going to use, you plug in all your work so I can see your numbers and your labels so that if you make a mistake, I can figure out what you did. It makes a difference in me assigning partial credit. Okay, another one. If the kinetic energy of a 4 kilogram shot, 4.00 kilogram shot, is 13,570 joules, boy, this is supposed to say how fast is it moving? Has mass. Who knows? Okay, how fast is it moving? So I'm going to go back to kinetic energy equals 1/2 mv squared. And if I'm looking for how fast, I want to find this. So I move everything else. I'm going to take my 2 times my kinetic energy divided by mass equals my velocity squared. So then I take the square root of everything, and that's going to give me V equals square root of 2 times 13,570 joules over 4.00 kilograms. Okay, let's try to take a look at our labels. I'm going to just break this out on the side. A joule is a Newton times a meter, and we're dividing this by a kilogram. But a Newton is a kilogram times a meter per second squared, so the kilograms cross off. And I'm going to be left with meters squared over second squared. That's under the radical. So when I take it out of the radical, I'm going to have meters per second. We got to think about our labels. The labels work. It's a velocity label. Don't just assume that the labels are going to work. Check them out. So I am going to take square root of 2 times 13,570 divided by 4, close my parentheses, hit equals, and I've got a velocity of 3 sig figs. It's got 4, that's got 3, so I can go 3 sig figs. 82.4 meters per second. Whew. I think I was a little I guessed on some numbers. I guessed way wrong. Oh well. This must not be a shot that somebody's putting. This must be a cannonball. There we go. Yeah, that's what I had in mind all along. All right, let's talk about potential energy. All right, so kinetic energy was energy in motion. And then sometimes students tell me potential energy is energy that's not in motion. I need more than that, okay? Potential energy is energy an object has stored in its position or condition. How can you do that? Look at this stick. I can bend it a little bit, and when I let it go, oh, hey, gee, that stored in that position. I'm not only storing energy in the stick, but I'm storing it in the tendons, I think, in my arm and hand. Oh, I'm storing some energy. When I lift up this shot, okay, I stored some energy because, just kidding. We can store energy. All right. How do we calculate it? Oh, gravitational potential energy is that second one where I said it's stored in its position. Oops, I went the wrong way. Energy stored in objects height above the Earth or whatever planet you happen to be on right now. Gravitational potential energy. If I were going to, well, let's go through this example. Let's say I'm going to drop this shot on your toes, but you get to choose what height to drop it from. Well, if you're smart at all, you're going to choose to drop it from over. Now, Ian, I can hear you out there. You're saying, well, drop it from up here. No. If you're being smart about it, you're going to drop this just barely above your toes. It's not going to have much energy in that height, okay? Now, if I said I am going to drop it from way up here, you'd probably prefer if I dropped the tennis ball on your toes rather than the shot, okay? Different mass. And if I was going to drop this shot on your toes from way up here, you'd probably prefer if you were standing on Pluto versus standing on the Earth when I did that. Although there might be some other disadvantages about Pluto. You know what I mean. All right. How do we calculate it? Gravitational potential energy, so I went potential energy, sub G for gravitational, is mgh, where m is the mass, g is the gravitational acceleration of your location, usually the Earth, and h is your height above the Earth. And if we look at labels, we got kilograms, meters per second squared, and meters, that's going to be kilogram meter squared per second squared. That's a joule. All right, what is the gravitational potential energy of 12 kilograms of water, 12.0 kilograms of water propped over a 2.00 meter high door? Knock, knock, come in. Funny guy. All right. You wouldn't believe how many times on April 1st I've thought about doing that right over here. Okay. Dreaming time over. So, gravitational potential energy is mgh. So we've got 12 kilograms of water, 12.0 kilograms, times G is 9.80 meters per second squared, last time I checked, and the door is 2.00 meters high. Kilograms times meter per second squared is Newton. Newton times meter is a joule. Get used to your labels. 12 times 9.8 times 2 equals, and we get 3 sig figs. So I've got 235 joules. Okay. The surface of the moon has 1/6 the gravity of the surface of the Earth. When a 56 kilogram astronaut is standing on a lunar ledge, she has 680 joules of energy more than when she is standing on the surface below. How high is the ledge? Well, we know we're dealing with these energies, and I've got an energy. Why does she have energy? Because she's up height. So I'm going to use gravitational potential energy is mgh. This time I'm looking for the h. So h equals the gravitational potential energy divided by m divided by g. And we were told she had 680 joules of energy. And she's got a mass of 56 kilograms. And G is 9.80. Oh, well, I could do that. 9.80 meters per second squared divided by 6, 1/6 of that. So if I divide that by 6, then it's already in the denominator. That 6 comes back to the numerator. Now, if that doesn't make sense, you just go off on the side, take 9.80, divide by 6, get that number and plug it in right there. But this works. It's 9.80 divided by 6, but it's in the denominator, so it flips over. Labels. A joule is a Newton times a meter. A kilogram times a meter per second squared is a Newton. So all of that's gone. I'm left with meters. Good news for a height to be measured in meters. 680 times 6 divided by 56 divided by 9.8. Only got 2 sig figs this time, so it looks like her ledge is 7.4 meters above the surface. As always, formula, okay, there's my starting formula, here's my working formula. I get to my working equation, plug in my numbers with my labels, calculate it out. So, elastic potential energy. Give me a second here. Here we go. Elastic means that when you deform it, it wants to go back to its original shape. Okay? So here's a rubber band. Rubber bands are elastic. Okay? A basketball is elastic. This tennis ball is elastic. If I deform it, it wants to go back to its original shape. Actually, you know, if you ever watch tennis, it's not something I've done a whole lot of, but on a serve, the tennis ball can be well over, I think, 100 miles per hour because you get that collision between the ball and the racket. In that very short period of time, you're storing a lot of energy both in the ball and in the stretch of the racket itself, and then that energy all pops back into the kinetic energy of the ball. So, in this case, it's not about how high above the earth, it's about how much it's deformed. Okay? Now, not all objects deform very well. If I take this sponge and I squeeze it, it deforms, and it does kind of sort of come back to its original condition, and if it wasn't a really old ancient sponge, it might come back a little bit better than that. but they come back somewhat slower, okay? So it absorbs energy. I don't know if any of you have ever tried pole vault, but when you land on the mat absorbs, and it does go back to its original shape, but it goes back a little bit slow, and so it helps to dissipate the energy. We're going to find out that energy can never be lost, but it can dissipate into the background. All right, how do we calculate elastic potential energy? This formula looks a little weird. Elastic potential energy is 1/2 K delta D squared, where K stands for the spring constant. Okay, so the actual object has some inherent properties and one is called the spring constant. Spring constant is often given as newtons per meter. This delta D is the distance that it's stretched or deformed. And so delta D squared. So let's practice it. A slingshot has a spring constant of 125 newtons per meter. What is the elastic potential energy when it is stretched 65.0 centimeters? So, the elastic potential energy equals 1/2 K delta D squared. So we've got our 1/2. K was 125 newtons per meter. Delta D is 65.0 centimeters. Did you catch that? This had a meter in it. I don't want to put meters and centimeters in there, so I'm just going to do a very quick mental conversion. I know that 65 centimeters, move the decimal point 2 places. That's 0.650 meters, and that value is squared, so 0.650 meters. Now, I hazard that if you're not putting your labels down, some of you would miss that. Put your labels down. Make sure that they cross off. In this case, I can cross off one of the meters. I'm left with a Newton times meter, which is a joule. And I'm going to start out with, well, okay, I can do 1 divided by 2 times 125 times 0.65 times 0.65 equals 26. I got 3 figs, so 26.4 joules. Okay? All right. A spring is compressed 23.0 centimeters when it has a potential energy of 165 joules. What is the spring constant? So, elastic potential energy is 1/2 K delta D squared. In this case, I'm looking for K. So I'm going to multiply by 2. 2 times my potential energy divided by delta D squared equals K. So 2 times my potential energy of 165 joules divided by delta D. Again, I got centimeters. Let's get rid of that. Let's just go 0.230 meters. 0.230 meters again. Squared. A joule is a Newton times a meter, which means that one of those meters cross off, and now I have newtons per meter. Huh. Well, let's take another step. Oh, no, I don't have to take. I said that the spring constant is often in newtons per meter. All right. 2 times 165 divided by 0.23 divided by 0.23 equals, and we've got 3 sig figs, 6,240 newtons per meter. All right. So I try to do 2 sample problems from each of those types of energy. I got just one more term here for you, and that is mechanical energy. So what if you imagine, this ball is flying through the air. It is moving, so it'd have kinetic energy, and it's above the ground, so it's got potential energy. And I imagine we could come up with situations where there's elastic potential and gravitational potential, everything all combined. So this is a kind of a catch-all term. It's not really a different type of energy. It's just a category saying it includes all of the kinetic and relevant potential energies of an object. Okay? So when this ball is traveling, it may have both kinetic and potential energy, and we group that together into a concept we call mechanical energy. All right? I don't know how long this video has gotten, but it's long enough. That's quite a bit for you. Hopefully it's going to help. If you got a little bit stuck on yesterday's exercises because I didn't have a video for you yesterday, hopefully this helps you go back and take a look. And I'm going to give you a couple more practice problems. Because it's a longer video, I'll try to keep the practice problems light. And as always, if you have questions, please let me know. Take care of yourselves. Stay safe.